So let's start our study of rotational motion. And we'll do that by revisiting some quantities that we picked up in circular: angular velocity and angular acceleration. Now we're talking about rotation of rigid bodies, and so we need to define that. So that's just an object which doesn't bend, twist, stretch, etc. So rods, like the human forearm, anything that's solid and it's going to be moving about axis of rotation. So like in this case, you have this like metal bar, and then it's attached by some sort of like screw to a wall or something. I don't know, or the hand on a clock or whatever. Point is that the whole thing moves all together around some axis of rotation. So in this case, the axis of rotation would be right through this point. So that'd be the axis of rotation. And then suppose this thing is rotating, around this way. So it's going to swing around and do circles. So that's what we talk about, or that's what we're talking about when we say the rotation of a rigid body. And the first thing we need to do is just talk about like, where is it? So angular position. And so that would be a theta. So it's going to be an angle. And we would measure it off of the positive x-axis. So something like this. So if we said that this was x, then we could say that the angular position, theta, is given by that angle there. Theta is in radians. So again, this is all stuff that we picked up in circular motion. And just to go over what a radian is again, is if you sweep out an angle such that the arc length S, so this would be S, so the arc length is equal to the radius, then that's defined as 1 radian. So theta is the ratio of S to R. So if they're equal to each other, then you get 1 on this side. So that's 1 radian. 1 radian is whenever this equals this. And we'll use this in order to do some conversions. So if you want to know linearly how far you are, well, then you would just multiply the radians times the radius, and that would be your position, your linear position. So the arc length that you've carved out. We'll use that in an example here in a bit. Okay, so that's angular position. Just make sure you put everything in radians. Otherwise, your kinematics and stuff won't work. Now we get to angular velocity. So we have something, it's moved through some displacement. We want to know how fast. Remember that velocity is just change in position over time. And so we have a new well, it's not really new. We did it with circular. So we're going to have angular velocity, omega, which is going to be the change in angular position over time. But this is an average, because maybe it's changing. So now we can introduce some calculus. So the instantaneous angular velocity would be the limit as delta t goes to 0 of the change in position over time. And we know that that is called the derivative of angular position with respect to time. So let's talk about 2 points on this object. So we have point A and point B. And this thing sweeps out an angle, theta. So the whole thing rotates. It rotates this way, and it carves out some angle theta. The angular velocity for both of these things is going to be the same, because they both moved through the same. They say they have the same initial and final position, angular position. However, if you look at the path that they carved out, you can see that B carved out a lot more. So the arc length here for B is greater than the arc length for A. And since this thing doesn't bend or twist, we know that this one covered the less distance or this one was greater distance in the same amount of time, so this one had to be going a lot faster. So in this case, the angular velocity of B is equal to the angular velocity of A. And in fact, every point on here has the same angular velocity. However, the tangential velocity or linear velocity of B is greater than the velocity of A. And that's because we have to multiply by r. If you recall that our tangential velocity is going to be omega times r. And since r is bigger for B, we get a larger tangential velocity. So this should be familiar from circular motion. The other thing to know is direction. So same thing as circular. I think we talked about it in class. But if an object is rotating this way, then that's positive. And if it's going the other way, that's a negative. So those are your directions on your velocities. And we use the right-hand rule, but I'll get more into that in just a second. So let's go through this example and see how all of this plays out. So the angular position on a flywheel is a part of an engine. Let me see. I was going to use a helicopter, but I didn't like the pictures. Let me see, flywheel. See if I can get a good one for you. Oh, here you go. So there's a flywheel and an engine. So when the engine's on, this thing, it spins around and it kind of keeps everything turning. We'll talk when we get to energy. We can come back and visit flywheels. They make some cool toys. Let me see, flywheel toy. I'm trying to see which ones we have around the house. I don't know. But they're the types of cars that you rub against the floor over and over, and then you let it go and it goes zoo. Those are using flywheels. All right. Anyway, so the flywheel, the position, we have a position function, and so it's 2 radians per. The units on angular velocity, of course, are radians per second. Just get that in there. So these are radians per second cubed times time cubed. So you see the cubes cancel, leaving just radians. So we're all good. The diameter of the flywheel is 0.36 meters. Find the position at 2 seconds and 5 seconds. Find the distance a point on the rim travels during that time. Find the average velocity from 2 to 5, and find the instantaneous at 5 seconds. Okay, well, the position at 2 and 5 is pretty straightforward. I don't even know if I want to go through it, but that would just be a substitution. So theta at 2 seconds would be 2 radians per second times 2 seconds cubed. And that would be, 816 radian. Omega at 5 seconds, theta, is going to be the same thing, so 2 times 5 cubed. You should really put units in there, but that's fine. So 5 times 5 times 5, 125 times 2, 250 radian. All right. The other thing you might do is maybe you want to convert this into degrees. So to do that, we just do some unit conversion. 2 pi radian. That's all the way around the circle, is 360 degrees. And that would convert it into degrees. Okay. B, find the distance a point on the rim travels during that time. So it goes from 16 to 250. So the total change, B, the change in position would be 250 minus 16, which would be 34, 234 radian. And then we want to know out at the edge. So all the way out at the edge, how far does this thing go? And the distance there, the diameter is 0.36, so the radius is 0.18. Be careful with that. So that's going to be my r. And then we know that theta is going to be s over r, and we're looking for s. So my linear position is going to be r times theta. So 0.18 times 234. All right, so multiply that out. I don't know, it's like 42 or something like that. So 42 meters. Now wait, you might say. This was meters, this was radians. How come it's not meter radians? So actually the theta is unitless. When we put radian here, it's just for our own sake, so that we know that this is we're measuring in radians. But it's a unitless measure, because our S and our R, that would be meters over meters, and those would cancel out. So there really are no units for degrees measured in radians. So we're all good. All right, C, find the average velocity over the same time. So average velocity would be the change over the time. Omega average. That would be my change in position over my change in time. Change in position we already calculated, so that would be 234 over the time, 2 to 5 seconds, which is 3. So we get that the average angular velocity, 78 radians per second. And we may need to convert this to say like revolutions per minute. So that would be 78 radians per second times 2 pi radians. It's 360 degrees, but that's also just one revolution. Times seconds. There's 60 seconds in 1 minute. I'm not going to calculate it, but the seconds cancel, the radians cancel. So you get revolutions per minute. So RPMs. All right, and then finally D. Let's find the instantaneous at 5 seconds. It was 2t cubed. So theta was given by the function 2t cubed. We want to know the instantaneous, which is the derivative of the position with respect to time. And so that would be 6t squared. That would be omega. So omega at 5 seconds, it's going to be 6 times 5 squared. So 25 times 6, which is what, 150 radians per second. And that covers most aspects of it. Okay, so we kind of defined what it was, what angular velocity is. We talked about direction, but what about it being a vector? So how are we going to deal with the vector? And so this gets a little tricky to draw. It's easier to do in person, but what we're dealing with is we're actually dealing in 3 dimensions now. So we have, I'm going to show you how to draw the x, y, z plane. So your x goes across, still goes across. That's your x. And then y, what you do is we'll define that at 0. Y is at an angle. So it's going to come across like this. So like this would be your y direction. That goes into the page. And then z comes up out of this. So z is like right in here. So that's your z. Okay, so what we're going to look at is an object which is rotating in the xy, the xy plane. So it's attached here at the origin and then comes out like this rod. Okay, and then let's say it's rotating through in the xy plane, so it rotates around maybe to here. Oh, by the way, these are the positives. Okay, so we have this displacement. How do we define the angular velocity? So the angular velocity is a vector, that actually points perpendicular right along the z-axis. So this vector right here, this is the angular velocity vector. And what we calculated, like how fast this thing is going, that's actually the angular velocity about the z-axis. That's what we were talking about. That's the displacement over time and all of that stuff. So it's a component of it. And the thing is that this is the only component here if the axis is not moving. So if we don't have a change in the orientation of the z-axis, then everything's good. Whatever we do is going to end up being that vector. But later we'll see what happens, you know, if this thing starts moving around, like gyroscopes and stuff like that. So we'll come back to it, but just know that the actual vector, it's perpendicular. So how do you know which way this goes? Well, that's the right-hand rule. So since this thing is going in this direction, using the right-hand rule, that would be a curl this way with your thumb pointing up. And so these are your fingers. I know I'm not drawing it. Can't draw hands. Oh, that's not that bad. Okay, so your thumb points up if you curl your fingers this way. Now, if it was rotating in the other direction, so if we had a rotation in this direction, well, then you would have to curl your fingers the other way. You'd have to curl them this way. I can't draw this. Point as your thumb points down. All right, good enough. And so this would be negative. So your vector would point down. So the vector actually points in the direction of your thumb. That makes sense. It's easier if I just show you in class. There's other ways you can think about it, or you can figure it out. No, I don't, never mind. Forget that I said that. All right. Let's talk angular acceleration. Sorry, I'm trying to write fast. Angular acceleration, we use alpha. And the average angular acceleration would be the change in the angular velocity with respect to time. However, we know calculus, so the instantaneous is going to be, again, the limit as delta t goes to 0 of the change in the angular over time, and we know that as the derivative of the velocity with respect to time. And the velocity is the derivative of position, so we could say that it's also the second derivative of angular position with respect to time. So you should recognize those. It's the same as we did with linear kinematics. The angular acceleration, it's also a vector, and it will just depend on the sign. So if the signs of angular velocity and acceleration are the same, then it's speeding up. And if they're opposite, it's slowing down. And so then the sign just tells you which way it points. It's the same rule. If it's positive, it's up, or if the angular acceleration, not necessarily. So yeah, we can just use the sign on the acceleration to indicate the direction. Or if you know it's speeding up or slowing down, it's going to be the same or opposite of the angular velocity. All right, I'm going to set up an example and then we'll be done with this section. So what we'll do is we'll use the same situation as before. This is the flywheel that we just did. So the position function. So let's get first, let's figure out what we want to know is the average angular acceleration and the instantaneous from t equals 2 to 5 seconds. And instantaneous, whatever, you know what I'm doing. Okay, so first thing, so the angular acceleration is the second derivative of the position with respect to time. Or it's the derivative of the velocity. So we need to take the derivative of that to get the velocity. Let me write that out. So omega with respect to time. So let's get omega. So omega, we already did it. We take 3 down, so that would be 6t squared. And then the derivative of this with respect to time is going to be 2 times 6 is 12t. And that would be our angular acceleration would be 12t. And now we can find, so the average would just be that would be the acceleration at 5 seconds minus the acceleration at 2 seconds. So it would be 12 times 5 minus 12 times 2 divided by the change in time, 5 minus 2. So whatever that calculates out to be. I'm just using this at the 2 times, the time final, time initial. All right, our instantaneous acceleration, keep drawing A's, at 5 seconds would be the function at 5 seconds. You know what, I did this one, we should have done this using the velocity, sorry. The average is going to be the velocity, the change in velocity with respect to time. So the velocity would be 6 times 5 squared minus 6 times 2 squared over the same time period, 3. And that would tell me the average. Sorry about that. Ignore that. All right, and that's it. All right, so you'll have some practice problems.